2 seconds. That's how long it takes for Docker Run to give you an isolated environment with its own file system, its own network, its own process tree. A virtual machine doing the same thing? 30 seconds, sometimes over a minute. Both give you isolation. Both let you run software in a self-contained environment. So what's actually different about them? A container is not a small VM. A container is a regular Linux process that the kernel has been told to lie to. And something you do every day, Docker exec, is actually much simpler and stranger than you think. Quick context. Before any of this, multiple applications shared one server, one OS. Library conflicts, resource contention, one app's vulnerability exposing everything else. Virtual machines solved that by faking entire computers. A hypervisor creates VMs, each with virtualized hardware and its own complete operating system, its own kernel, its own libraries, the full stack. 3 VMs means 3 kernels in memory. That full separation is what makes VMs well isolated. An attacker who compromises one VM is stuck inside it. Escaping requires a bug in the hypervisor, a very small attack surface. Modern CPUs have dedicated instructions, VTX and AMD-V, that make virtualization fast. CPU overhead is typically 3 to 5%. The real cost is in memory, boot time, and disk and network I/O, where virtualization layers add up. VMs are still the backbone of cloud infrastructure, but if you just need to isolate one process, do you really need to boot an entire operating system? You'll hear containers called lightweight VMs. That's misleading. Let's look at what they actually are. A container is a process, a regular process running on the host operating system, same kind of process as your shell or your text editor. If you run a container and check your host's process list, you'll find it sitting right there. Normal PID, normal process table. What makes it a container is that the kernel wraps this process in a set of isolation mechanisms. The process behaves as if it has the machine to itself, but it doesn't. It's sharing the host kernel with every other container on the system. 2 kernel features do the heavy lifting. Namespaces control what a process can see. The best way to understand them is one at a time. Normally, every process on a Linux machine shares one global list of process IDs. A namespace PID gives the container its own process tree. The main process inside sees itself as PID 1, as if it just booted a fresh machine. On the host, that same process is PID 48372. Same process, 2 views. Keep this in mind because when we get to Docker exec, you'll see that getting a shell inside a container is nothing more than starting another process with the same namespace assignments. Mount namespaces are why a container sees a completely different file system than the host. When you Docker run Ubuntu, the process doesn't see your host's root directory. It sees the Ubuntu images file system mounted as root. Same kernel underneath, different view of what's mounted where. This is what connects container images to what's actually happening. The image layers become the mount namespaces file system. Network namespaces give containers their own IP and ports. 2 containers can both bind to port 80 without conflict. User namespaces can remap user IDs, so root inside the container maps to an unprivileged user on the host. That's all namespaces are, the kernel deciding what each process is allowed to see. Namespaces handle visibility. cgroups handle resources. cgroups, or control groups, let you set hard limits. This container gets at most 2 CPU cores and 1 gig of memory. The kernel enforces the tap. This prevents one container from starving everything else on the system. Podman, Containerd, and others use the same primitives underneath. The shared kernel is a shared attack surface. If someone finds a kernel vulnerability, a container can potentially break out. This isn't theoretical. In 2019, CVE 20195736 hit runC, the low-level runtime that Docker and Kubernetes both use. A container process could overwrite the host's runc binary and gain root on the host machine. It was patched, but it proved the attack surface is real. For most workloads, container isolation is fine, but when you're running untrusted code from different customers on the same machine, containers alone aren't enough. AWS Lambda uses Firecracker, a purpose-built lightweight VM, to isolate each function's execution environment. Different functions and different accounts always get separate micro VMs. Multiple invocations of the same function can reuse one. That's what a warm start is. Fly.io uses Firecracker too. Google Cloud uses gvisor, which implements an entire application kernel in user space, re-implementing Linux syscalls so they never reach the real host kernel. The pattern: when you can't trust the code, you add something stronger than namespaces and cgroups. Now, here's one that connects directly to your daily workflow. Containers are a Linux kernel feature. Your Mac runs the Darwin kernel, Windows runs NT. Neither has the features containers need. So Docker Desktop creates a lightweight Linux VM in the background. Your containers run inside that VM, not on your Mac directly. That's slow volume mount performance when developing locally. Files are being synced across the VM boundary, roughly 3 times slower than native Linux, even with the latest optimizations. Networking quirks? Traffic routes through the VM. That small performance gap between local and production? Same reason. Docker Desktop handles all of this, but knowing why it happens means you stop chasing bugs that aren't in your code. Everything I've said, containers as processes, namespaces as the isolation mechanism, you can see it yourself. Start a container, Nginx in the background. Check PSAUX on the host. There it is, your container, in the normal process list with a regular PID, not inside a virtual machine, not in a special sandbox, a process. Now look at /proc for that PID in the NS directory. These are the actual namespace links the kernel attached to this process. Mount, PID, network, user, they're all here as symlinks, each pointing to a namespace identifier. This is what makes it a container. Not Docker, not a runtime, these namespace links on a Linux process. This is what ties it all together. No Docker, no container runtime, one Linux command, unshare, and this process thinks it's PID1 on a fresh machine. PS shows 2 processes. The host's thousands of other processes are invisible. This is what a container is at its core. Docker wraps it in image management, networking, a nice CLI. But the kernel mechanism is what you're looking at right now. Last thing, that Docker exec I mentioned at the beginning, getting a shell inside a running container, the runtime calls a single Linux system call, setns, which just means take this new process and put it in the same namespaces as that existing one. Same file system view, same network, same PID tree, same cgroup limits. There's no box being entered, no boundary being crossed. VMs virtualize hardware. Each one runs its own kernel. Containers virtualize the operating system. The kernel uses namespaces and cgroups to isolate ordinary processes. In production, you usually use both. VMs for the infrastructure boundary, containers for application packaging. Complementary tools for different layers. That's really all it is. If this was helpful, a like helps other developers find it. Thanks for watching. See you in the next one.